No, so everyone, I'm on the screen share. Oh, can you ask them to go away? All right, I'll ask them better. Not quite right, is it? No. Mm-hmm. All right, let me see if I can fix the audio quality, video quality. It looked fine before, right? It's just a little bit of the right is missing. I think it matters. I think that you can read everything of your presentation. Yeah, I think. Yeah, but it's only this one slide. It's just, yeah, so I realize it's your name, which is annoying. Sorry, but the rest of the presentation you can read all the slides. Okay.
I think Tom said you were a bit late, but he told us to just start.
Oh, okay. Cool. Thanks for coming. Yeah, okay. Let's start. So, yes, welcome everyone. Thanks for coming to Guyver's presentation. First time we'll hear Guyver speak about the stuff he's been cooking up in deep learning. It's been very interesting for me to watch because it's a little bit outside of my area, and I'm very glad that yesterday, day before, Tom agreed to be on Guyver's panel. Tom's got a lot of experience in deep learning, so now we're feeling a bit more confident.
Tom is just outside.
Okay, we'll expect him in a couple of minutes. But yeah, tell us what you've been doing.
Yeah, so good morning, everyone. I'm Guyver, and welcome to my thesis proposal review presentation. So my topic is in continual learning and deep learning. And
sorry, keep talking.
My panel members consist of Josh Milford, Greg Felson, who's from University of New England, and Tom Gideon. So I'll briefly go over some terminology and concepts that will be useful for today's presentation. So deep learning has many useful applications. So for example, one that perhaps is the most famous is AlphaGo, which is an AI that Google developed in 2015 and 16 that was the first to be a Go grandmaster. So they continue to build on that and have a new system, which is AlphaZero, as shown in the diagram, which not only able to play Go, but was also able to play games like chess and shogi. Shogi is a Japanese version of chess. So in supervised learning, we're given a dataset D, which have pairs of input and output. So X will be our input feature vector, and Y is our output vector. So for example, in the AlphaZero case, our input X will be something like the game states that we're in, and the output will be the probability of the best moves to do. What we want is, given that when we have a new game state, we want to be able to predict what's our best probability vector. So, for example, in this case, we are given with new game state and the AlphaZero case, and we're trying to predict a good probability vector. And this often requires a large amount of data. For example, in the AlphaZero case, they will train on millions of different game states. So a brief overview of neural network and transfer learning. So on the left, we have a deep neural net, which consists of quite a few layers, and every layer is fully connected. So in transfer learning, what we want to do is we freeze essentially most of the network and retrain only certain part of the network. So on the right, we have we're only retraining on the final layer. So as you can see, most of the parameters is actually freeze, whereas only the last layer is retrained. So this will mean that we'll have faster computation time as there's less parameters to train on, and also likely to require less data. So in the case when we have transfer learning, we want to apply close things that are in a closed domain. So it's quite natural to think of these similar concepts as different tasks. So we'll define tasks as a free tuple, which is defined by an input set I output set O, and the true mapping from the input to output. So here we have an example of 10 written digits for Arabic numerals and Chinese numeral. So on the top, we have input set 1, which is our Arabic numerals. And on the bottom, we have a different input set, which is our Chinese numerals, input set 2. These actually have a common output set, which is just the numbers from 0 to 9. And we have our mapping for the Arabic numerals to the output as in 1, which is different to our mapping in 2 to from the Chinese numeral to the digits. So for example, on the left we have 3, and that will be mapped to 3 for the Arabic numeral, whereas this mapping is not necessarily true for the Chinese numeral. So we're more likely to have something like on the bottom right, this character will be mapped to the character 4.
Remind in Arabic, in 9 Arabic, the circle on the top is on the other side.
Yeah, that was a quite weird. So it's like a rotated, and they also add noise to the image.
So it's not even rotated, right?
It's like
yeah. In fact, you did find this,
yeah,
right? In this data set, there is at least one with over 9. It looks like an accident. As you say, it doesn't look like a 9.
Yeah.
Which makes me worried sometimes about the, you know, that when people get 99.9% right on this, how is it possible that there are errors? Yeah, yeah.
So with mentioning of new tasks, what likely, so if we use something like transfer, the not basic shallow transfer learning, when we learn a new task on the same model, what's very likely to happen is that the performance for our previous task deteriorates when we are learning a new task. And this is known as catastrophic failure. So we can look at some examples such as in the Atari game. So in this case, our input will be the game screen, and our output will be the controls for the next move. And in this case, so we first train on the top game, which is Pawn. And then after that finished training, and we'll get a good score against the human players, we train on Alien, which is a different Atari game, which is shown in the bottom screen. And after we finish training on Alien and be able to get a good score for Alien, we are likely, if we apply the model to Pawn again, it's likely to have a lot worse performance than when we first train on it. And this is likely due to, say, in the image we can see they both have similar white dots on Pawn and Alien. So for Pawn, this is the ball that we're trying to bounce to the other side, whereas in Alien, these are the alien eggs that we're trying to destroy by going towards them, just like in Pac-Man. Another example could be image classification. So our first task might be training on classification of different car models, and then our next task might be training for different plane models. So when we're learning the plane model, we'll probably learn the concept of wings, whereas this concept doesn't exist for car. So if we apply the car data set to this new train model, we are likely have unexpected behaviors which will deteriorate the performance. So one way that we could try to avoid this is by having naive multitask learning. And this is just simply having different multiple models for each of the different multiple tasks. But the main problem with this is that we'll have to be able to design the models for each of the tasks, and this will require we needing to tune for each of the models, also training, which take computation resources and time, and also likely to have a lot of data set required for training them. So wouldn't it be very useful to have just one model that is able to learn multiple tasks without forgetting the past tasks? And this is essentially what a continual learning system is trying to do. So continual learning is commonly defined as the ability to learn over time by accommodating new knowledge while retaining previously learned experience. So the new knowledge we can think of as the new task we're trying to learn, and the previous learned experience is our previous learned tasks. So having defined all these terminology and concepts, I would like to state my thesis statement, which is that continual learning in a deep learning system, when applied to multiple tasks, can provide faster training time, automated neural structuring choices, and require less data to train, while still achieving accuracy comparable to a single task models. So single task model is like the naive case when we have just individual models for each different task. So next we look at some impacts and advantages of continual learning system. So first, in a continual learning system, we're able to inference for multiple tasks. So on the top, we have the naive case when we have separate models, individual models to do each of the tasks, whereas at the bottom, what we have is just one model that is able to do inference on both tasks. So we can also see from the bottom picture that there's less nodes and edges, which means there will be less memory required. So this could be quite useful when we are deploying into highly constrained embedded systems such as camera sensors, when we have limited memories available. And having this weights and nodes to train on, which means that we will usually have a lower training time, less computing resources needed, and lower data requirement. So the World Health Organization predict that by 2050, our production for food is likely to be able to keep up with our human population growth. So this means that agriculture is being pushed towards a digital paradigm, which means that there will be increasingly available fine-grained real-time sensor data collected in different farms to aid in things like automation, such as irrigation. So in irrigation, traditionally what they might do is irrigate every day except for days that been raining, but this is probably not very good, as the land may be have not enough water or too much water when they're just constantly irrigating. So instead, having the sensors means that we are able to collect soil moisture data and irrigate at the right time so that the soil moisture is kept at the optimal level. And also, for example, in the image, we can see there's two water sparklers. What we may be able to do is that the different part of the field have different moisture, and then we can control the water flow to the different sparklers to provide the right amount of water for different part of the field. Other automation can also be done, such as for seeding. So if we just also always seed at a constant time, that may not be the best depending on the climate we're in. So having sensor data from such a temperature, we're able to find better time to do our seeding. So if we seed too early, then the seed doesn't actually grow as well. And if we seed too late, by the time the season ends, we may not be at maturity. Automating harvesting is also a useful thing that they're trying to do in digital agriculture. So on the left, we have some corn crops that is just at their maturity, which is when we want to harvest. Whereas on the right, we have delayed harvesting, which means the plants start to decline. So these automation will bring us good impacts such as higher yield as mentioning and harvesting and seeding, and also things such as better animal welfare. So for example, here's an image of the Darling River system when over a million of fish has died due to the excess runoff from the farms that is likely to cause the algae bloom in the water, and which take up too much oxygen so that the fish cannot breathe, which is not very good welfare for them. And also if say the livestock drink water from the pond with a lot of dead fish is likely to cause them diseases as well. So kind of related to previous point is environmental sustainability. So for example, in irrigation, if we control our water use, we can reduce unnecessary water use. And so that means our water will be more sustainable. For example, here's an image of a polluted stream that getting too much emission from the neighboring farm and also too much excess water use. Having better information, I'll say our yield will means that we're more able to plan for our logistics, such as how we get our farm output into the market. So in this case, it means that we can provide fresher food to market faster and also reduce transport costs. So that will also be less emission, which kind of lead back to having a better environmental sustainability. And relatedly, if we can get fresher food onto the market, it will mean that our food quality will be better. And kind of mentioned earlier in the harvesting side, if we harvest at the right time, the food quality, again, is also higher quality than, say, if we have delay harvesting. So as agriculture setting is very highly diverse and also rapidly changing to stochastic condition, due to the complex, uncontrolled environmental situation they're in. And so here tasks will be quite complex. Example of this will be, say, camera captures of different signals of the same scene. So we can have different types of signals as different tasks. So for example, audio signals of the environment, say ambient noise or noise from the organism, can be considered as one task. And of the same scene, we can have just the capturing of the setting. Different environments can also be considered as different tasks. So in a farm setting, we're likely to have field that's near, say, a river, near trees, near livestock, or near just pasture land, so open land. So these are all likely to have different soil types. For example, on the left, we have rota soil, which is a more clay-like soil. And on the right, we have something like the tender soil, which is a slightly more sandy and less clay-like soil. And these two soil will exhibit different soil moisture properties. So we can consider them as different tasks and try to learn from one soil type into another. So one of the dataset I'm actually currently working on is the smart farm dataset from Grid, which is sensor data in the Kirby farm at Armadale. And in this farm, there's actually a patch of land that has quite different soil property to the rest of the farm. And having the ability to learn, say, for majority of farm and transfer this over into the different soil type will be useful. Different farms can also be considered as different soil tasks, as they will have different topology in their fields and also different climate that they're in. So next we look at some previous work that's done in continual learning. So as we mentioned earlier, catastrophic forgetting is the main issue when we're trying to tackle. So how can we prevent this? Currently, there's three main methods that people have been working on. So the first one is regularization, when they limit how much the weight can change so that they tend to try to limit how much they deviate from the previous learned tasks. Dynamic architecture is when the network is able to expand and grow in size to accommodate for the new features. And we also have two modes of memory, which is drawn from human brain trying to emulate the long-term and short-term memory. So in the diagram, we start at the section of the error. So we're at an optimal position for task A with low error. And with our regularization, when we're learning for a new task, we're likely to move towards the optimal of task B with the longer blue arrow. However, this means that we're now in a high error region for task A. Whereas if we apply regularization, we're able to, say, move in a shorter purple arrow towards somewhere that's low error region for task B and also for task A, which means that their performance will be reasonable for both tasks, rather than one being good and the other being terribly. Some example of this is L1 and L2 regularizers. So these essentially just limit how much the weight change when we're learning the new task. Fisher information value can also be used. So what this does is we learn on the previous, we see how much each weight, how important they are. And if they're very important, we try to not change them. And so you're penalized if you're changing it. So the disadvantage of this method is that the network capacity is still actually fixed. So eventually we'll meet bottleneck and unable to learn further. Another approach is the multiple modes of memory, as mentioned earlier, is drawn from the human mind. So one example is that they have weights that can have two different learning rates. For example, a long-term learning rate that is usually lower, and so they're less likely to make changes to previous learned tasks, or a short-term learning rate which is higher, and they're trying to change more rapidly to accommodate for the new task. Another example of multiple mode of memory is self-organizing map with short-term memory. So self-organizing map is an artificial neural network that uses computer learning and have short-term memory as exemplars. What this does is create a map of your input states that is organized by the similarity between the inputs, and the exemplars are fixed size that is kept for inputs that seem to be different from what's already in our self-organizing map. So again, this method still doesn't actually have more network capacity, except for the fixed state, for the fixed size short-term memory. The third approach is dynamic architecture when we grow the architecture in size. So example of this is the progressive network, as shown in the image. So first we start on the left with just an ordinary structure for our task 1. Then we're trying to learn task 2. And what we do is we duplicate task 1 and learn task 2, which is the orange blocks. So the dotted line means that these nodes are freeze when we're trying to train it, and the faded one means it's just irrelevant, as when we're learning for task 2, we're only using, say, the output for the task 2 architecture. And if we want to learn another further task, what we do is we connect the new task, the new model to the previous 2 tasks, and again, freezing the previous task. So dynamic expanding network is also another approach. So what they do is when they deem the new input to be too different, they add a constant number of nodes to each of the layer and selectively retrain certain number of nodes. And they will remove any nodes that they think is redundant. So the current method have one shortcoming, which is that they don't actually grow in depth. So next will be the proposal work. So first is task identification. So most existing method actually require tasks to be known. So for example, in the progressive neural case, we actually have to know when exactly we have new tasks so that we know when to do our freezing and our duplication. And also in the dynamic architecture usually, so having the new task is one of the indicator for the time when they will have to expand the network. One of the example that in literature is saying that they don't actually need to know tasks is shown on the left. So on the top, we have one task that's trying to identify between class A and E. And on the bottom, we have another task, say task 2, trying to identify between class B and C. So an inference, we will have the ground truth, and say both class E and Z will be outputting 4, and then we compare with our ground truth. We can do evaluation and calculate their accuracy. But if we were to inference in, say, a real situation, this is not particularly useful because we're given an unknown class and we run through a model, we get a value, say 2, but we don't actually know whether it will be something like class C or X. And if, say, the number of tasks we have grow, then this will become a lot more ambiguous as to what is the predicted class. So I propose to implement initially methods that, say, keep a list of exemplars to keep track of the inputs, and when new input comes, they compare with existing exemplars to see what is likely to be its task, or doing clustering on the inputs so that the new input will be compared to the different clusters and to see which cluster it fall into, when that will be considered as the task. Another method that I propose to look into will be using self-organizing map when the inputs are organized by dissimilarity. So when new input come in, we can see where in the region it fall into. Next will be analysis on different continual learning systems. So most existing literature only really consider on their classification accuracy, but they don't really have a fair comparison to other systems. For example, there will be other useful measures to consider, such as the speed of retraining. How long does the continual learning system take to retrain? How much data is required to train it? Also, the size of the model itself. And these can be compared to the baseline of when we do shallow retraining, which we initialize to, say, the previous task and then retrain from there, or partially retraining certain layers of the architecture, or even comparing to just completely retraining from scratch, from ground, from random initialization of the model. And so we'll compare stuff like accuracy, size, and speed to these baselines. Next will be the application. So most tasks in literature is rather artificial. So for example, kind of mentioned in the previous and the task identification slide, what they do is they have a data set such as Cipher 100, which is a 100 class image classification, and they will arbitrarily break it, say, into 20 tasks, which is by having each task as 5 classes. So we're looking into more agriculture settings which have high complexity class, such as identifying rare species. So in this case, what we're trying to do is we'll learn on more general, say, bee species, more general bee species which have more abundant data. And then when we're trying to learn the rare bee species, the continual learning system will try to construct new network structure that is specialized and identify special features of the rare species. Other things in the agriculture setting is like soil moisture prediction. So we can transfer from, say, different sensor types. So we might have abundance of temperature sensors, and we're trying to apply that into soil moisture sensor types. Or, as mentioned earlier, different soil types can also be considered as tasks. And the next thing I tend to work on is to increase the capability of expanding network. So other works currently only does duplication or pruning of fixed number of layers. So this means that the diff dimension is fixed and they only grow width. So I tend to build on this and come up with new method that will allow growth to occur in the diff direction rather than just width, as problems may be better solved by going deeper instead of going wide, where more parameters, exponentially more parameters may be required. So here's a timeline of what I tend to do. So first, I'll be working on task identification. As having our task identified, we'll be able to use firstly this information, such as task distance, to use as a deciding factor for expanding network. And after the task identification is done, I tend to do analysis on different continuing learning systems. And In parallel, we'll be working on expanding network. So after that is completed, I'll do the application in the agriculture setting. And throughout my candidature, I tend to do my thesis construction, as it will probably be more useful to spread the writing out through a longer period of time. Finally, there will be other tasks that will be undertaken, such as training courses, going to, say, lectures that might be useful, and other paperwork such as annual reports. And to summarize, deep learning have many useful applications, but it can be quite overwhelming to be applied due to the need of large data requirement, computation resources, and the needing to design the model. So we want to use continual learning system which try to ease this hardship. And I propose to firstly work on automated task identification, increase expanding capability for the network to grow in size, and analyze different continual learning systems to give a fair comparison between different methods and apply the continual learning system that I come with in the agriculture setting. Yeah, so thanks to my panel for the past year for their guidance, and also to Bo for the template for this slide, and everyone here, thanks for your time.
Question. First, I've got a comment, not so much a question. You go back to the very early slide when you were showing the freezing.
Yeah. So this one?
I was thinking right there.
All right.
Later you talked about two different kinds of data, and it struck me that that diagram implies that you're going to freeze from the top and stop at some level. Yes. But it occurred to me that the kinds of data that you showed as examples would give a different view as well. When you talk about the digits, right, the Arabic versus Chinese and so on, it's like kind of very similar. Yes. So you could see that you should freeze single way. But then later you talked about audio versus video. Yeah. And it occurs to me that that's what you don't want to freeze the first few layers, you want to freeze the layers in the middle. Yeah. You know, you want to find features, whichever way that data hits the features, but then the word combination of features might be more similar. And I have to say, I've never seen anybody freeze just the middle bits. That's for learning. So it's worth investigating. Yes. I don't think I've seen it done.
Yes, so I think certainly with like the transfer line, we can, so for example, not even just freezing middle. So for example, we might freeze like partially.
Yeah. Because like even the simple thing, I don't know if you've seen it, but like I haven't seen it. Yeah. I like the thinking ahead, and I like your comments about how to properly assess these things, because you're right, it shouldn't just be that classification. Because if all you care about is classification accuracy, then you should assume you have less data, therefore nothing else matters.
Yeah, I think the application in agriculture, where you have constrained power budgets and poor network connectivity and so on, yeah, it really motivates why
application cost and to construct some kind of a proper cost function or metric for going, you know, yes, I've got, you know, on this transfer learning thing, I've got 5% less accuracy, but that's outweighed by the 10% lower energy cost and 50% lower data link. But how do you decide on the balance between energy and data and classification accuracy? It might be domain dependent.
Yeah, I think a lot will also be like how willing the farmers is likely to take up technology. So, for example, if you're able to give them, say, like, for example, for scientifically, it might be a very poor accuracy. So not like, say, 99% but maybe just 80%, but the farmers are quite happy with it, and they're actually able to deploy it with reasonable cost, and they're much more likely to uptake the new technology.
Assuming like the balance between the costs, how much a network has to grow. If you can go to the slide before, I think digital agriculture. Yes, this one. So basically, what's interesting here, I think, is that it's true that in general, if you want to perform task 1 and task 2 concurrently, then it's better the bottom arrangement, right? Because you have basically less neurons and it's easier to train, less memory and so on. But if you don't want to perform them concurrently, then the first situation is probably better. So that's where maybe some considerations about the cost and how the actual classification problem has to be solved, I think may be interesting for finding the right balance.
Yeah, and I guess another, so one is kind of more hypothesis. So it could be possible that when we learn from a continual learning system, we actually get better performance than just individual model, because we'll have, say, a large bit that is shared between different tasks and very specialized. So for example, in this diagram, we have like the red part, which is specialized for task 2 and blue for task 1. Whereas in the individual model, we actually, if we compare, say, task 2 actually have more connections there. So it could be potential that I have better accuracy. And another, I think, point is that, like, yes, having different models could be useful if we don't want concurrently, but we actually have to design them. Whereas for the continuous system, we essentially design the first one and just let it evolve itself.
So with these dynamically expanding networks, you're adding different kinds of units and potentially have different path lengths in terms of the number of layers and so on. So how can you compute these efficiently, both when you're doing training and also inference?
So I think probably generally for inference, the computation time shouldn't be too much of a restraint. But for example, when we expand the network, one thing that I'm trying to work on is actually use tasks as a natural way to split our model into different computation nodes. So then they will be able to compute parallel at different computation nodes.
Yeah. So actually mapping the classification tasks to tasks in a task flow system might actually be quite a nice way of programming this.
And it could be maybe more, say, hierarchical. So for example, tasks might be similar, then they'll all actually be on, say, one part of the distributed system, and then that distributed system might have further nodes for even more specialized tasks.
Not really important, but just want to have a look at your time schedule again, because then we can here. So it's 2 years for the whole PhD.
Yeah, so it's from like now.
Oh, from then.
So I'm 1 year and 1 candidate.
It's one paper at the end of the.
Yes, sorry. So the star indicate papers, so I tend to write 4 papers for each of the main essentially contributions.
You're going to write 2 papers in the next year?
That will be the plan.
We better get to it. Is it realistic? How do you think now?
It's good to have those. It's good to have those. Sort of following on from Josh's question, it occurred to me that if you've got a strong application area and you're looking devices which you send to the farmers, you're only going to be able to update them at most once a year, right? So you could probably kind of estimate how much data they could collect in a year, and maybe your diagram where you show a frozen thing with some extra bit on top. Maybe the frozen thing is pre-optimized, burnt into the chip. And so all your device is doing is the extra learning, and then you somehow capture that at the end of every year. You see what you're going to build into the next one. Right, so you might be able to estimate at least how much, what's the maximum extra data you're going to get, probably what's the minimum extra data.
Yeah, so I guess one thing with the sensor data is they actually have just so much outage. So for example, for the smartphone data that I'm working with, they're meant to sample every 5 minutes throughout the year, but a lot of times they actually the sensor can be offline for weeks or even months.
Yeah, the point about pre-deploying with the pre-trained model is I think really important, going to whether farmers will want to use these systems. If you install your system and then you have to wait for 6 months before it starts giving you any predictions, it's not going to be very desirable for farmers. Whereas if they start giving you, reasonably accurate predictions straight away, and it improves with time as you collect more local data.
Yeah. The other thing that Guyver said was about the 80%. It occurs to me that if you weekly get an 80% correct prediction, if it's not consistently wrong, but differently wrong each time, then it's like a metaphor, right? And so we learn how much to rely on. So multiple 80% predictions are probably better than a mostly 99% prediction that occasionally.
Any more questions?
Thanks, everyone.
Yeah, screencast.